If you found the buried treasure, you would be a pirate too. Okay, so we're going to look at calorimetry again. And instead of looking at a bunch of numbers with it, because we know how I feel about numbers, I hate them. We're going to just analytically set this up, but we're going to extend this example into using kinetic energy as well. So let's take a look at what we have up top in the beginning. What we have is hot copper shot. Hot copper shot. Hard to say, but it's essentially, copper shot that you'd shoot out of like a buck shotgun. It's just copper, and it's very, very warm. Okay, it's hot to the temperature. It's placed into a calorimeter with some water, which is at a cooler temperature. Okay, who knows what it is, but like it doesn't matter. We are just going to set up the analytical equation to solve for the new final temperature of the water, or that equilibrium temperature. So let's just think of this. If you take hot copper shot, the copper is going to have some mass, so let's just call it mass of Cu for copper. Copper has some specific heat. We could look it up in a table, so specific heat Cu. And then it's going to have an equilibrium temperature, which is what we're kind of looking for, right? Minus the initial temperature of the copper, whatever temperature it was when it was hot. We have two other objects to consider, the calorimeter and the water. If we add the mass of the calorimeter plus the specific heat of the calorimeter, we know it is going to arrive at an equilibrium temperature minus whatever the initial temperature of the calorimeter was. Often this is like room temperature, but it could be whatever. Okay. And then if we actually have the water itself, we would say we have the mass of the H2O, we have the specific heat of the H2O, we know that is 4.186, and then it's going to wind up at some final temperature minus some initial temperature of the H2O. And this, because it's an isolated closed system, is just going to be equal to 0. So once you have this, this is the analytical equation you're setting up. You could just run on through and calculate everything out, put in whatever numbers you need until you solve for a bunch of numbers and a bunch of TEQs. Once you put all those equilibrium temperatures together, you put those numbers in together, you separate your variables and whatnot, and then you solve for TEQ, and the problem's over, just like we did in our last latent heat example. So nothing too crazy there, okay? This is a doable problem. If you're like, wait a second, what if the water is going to vaporize? Well, if the water is going to vaporize and you're still looking for the final temperature of the water, as soon as that water vaporizes, you know the final temperature has to be 100 degrees C, because the water can't vaporize until it hits that. If you wanted to do that, though, you could, but it's kind of a rote problem at that point. I guess what you could do in that problem is figure out, how much energy did you have, and then adding in a MLV for the latent heat of vaporization of H2O. It would be interesting to see what mass of water in that problem vaporized, because at that point you would know that the final equilibrium temperature would be 100, and you could figure out all that extra energy goes into vaporizing some amount of water. So you could figure out how much water you lost there, which would kind of be cool. Okay. Now, one other thing that we could do in a problem like this is, if I take this a bunch of balls of copper, I could heat them up on a hot plate or on a stove and then dump them into the water, right? But what if I just took a shotgun and just shot it into a vessel of water, and I stored all the energy there? In this case, I can use the idea that traveling mass has energy. It has a kinetic energy, right? We know that if we shoot this hot copper shot, or we just shoot the copper shot in general, because it is traveling at some energy, 1/2 mv squared, where this is the velocity and mass of the shot, or the copper. We've been writing Cu, so let's do that again. Cu and Cu. We know this is some energy added to the system. Normally, we just call this kinetic energy, but there's no reason that we couldn't call it heat energy as well. And if that's the case, then we could say, hey, look, this heat energy could be added into the system, and we could say that it is just another term that pops up here. we could say this is a 1/2 mv squared term that gets added into everything. So not only might it be hot copper shot, but we might be shooting it at the system to do this. So that's a kind of a cool thing we could do. Maybe we shoot the hot copper shot at such a speed that we're able to figure out how much mass is vaporized by putting the vaporization in here, knowing that the final temperatures of the equilibrium position is 100 due to the vaporization point. We could extend these problems more if we wanted to. But in the end, a lot of these problems are just you have a bunch of numbers, and you're looking for just one thing in the end. The real key here is just take your time with the problems, really think about what's going on, and meticulously follow your algebra and all of your steps as you're going through to make sure you don't accidentally miss a term as you're walking through something like this, okay? So this is just more of an analytical kind of a thought idea of how to go through more calorimetry problems. Nothing crazy to them, nothing crazy in the math, but we could, find amounts of mass that we might be missing, and we can't forget kinetic energies. But for now, this is finished. Next time, we're actually going to start looking into the actual thermodynamics themselves. We're going to start taking these idea of heat transfers and start pumping them into systems to see what kind of useful work we can do out of them. And we're going to start that by first thinking about length changes of objects as they heat up or cool down. But until then, until next time, adios and take it easy.